Today we'll have series resonance. First, what is resonance? So resonance happens when the reactance of the inductor and capacitor are equal. Take note, reactance of the inductor and capacitor are equal, not the inductance equal to the capacitance. We can equate the two because one is in henries, one is in farads. So we need to express it into a common term, which is the reactance. So we can equate it. We can equate them. Okay. So X of L can be expressed into 2 pi times the frequency times the inductance, while X of C, reactance of the capacitor, can be expressed into 1 over 2 pi times frequency times capacitance. Okay. So we're looking for the frequency. Okay. So we need to have frequency alone, the other side, and all the other parameters at the other side. So let's have the frequency at the left side, and this one, 2 pi and L, then the other side. So we have F of F. So F times F, F squared, then this will be 1 over 2 pi times 2 pi, so 2 pi squared times L times C. So this will be the result. We have F squared equal to 1 over 2 pi squared times the inductance times the capacitance. Okay, we are not looking for the square of the frequency. We wanted the singular or the resonant frequency, not the square. So we need to get the square root. So square root of f squared is just the frequency itself. Then square root of 1 is 1. Square root of this denominator is 2 pi squared. So we'll go out of this radical symbol. Then what's left is square root of L times C. So we have frequency equal to 1 over 2 pi times square root of LC. So at this frequency, our reactance for the inductor and capacitor is equal. So this one is called the resonant frequency. Okay. So here we have the impedance equal to resistance plus J X sub L minus X sub C. So the impedance is expressed here in rectangular form. So if X sub L is equal to X sub C, okay, that means this imaginary part is equal to 0. So it is as if that the impedance is equal to the resistance, since the net reactance is equal to 0, right? So what happens during series resonance is that the impedance is minimum. So if it is in minimum, the impedance is minimum, then the current should be maximum, right? Because they are inversely proportional. If we have the current versus frequency graph, this is your waveform. So this is the peak or the maximum current, okay? So during this point, we're going to trace the frequency, that frequency wherein the current is maximum. This one will be the resonant, this will be the resonant frequency, okay? So during resonance, again, current is maximum, okay? This happens in series resonance, okay? Current is maximum in series resonance. So if we go down to the left or to the right, we will reach the point where the current is 70.7% of the maximum. So if we're going to trace the frequencies, okay, wherein we have the 70.7% of the maximum, these are called the cutoff frequencies. So these two are called the cutoff frequencies. So one is the lower cutoff frequency. The other one is the upper cutoff frequency. Okay? So if we are talking about the current or voltage, look for the 70.7% of the peak. Okay? So this one is the 70.7% of the peak if it's in terms of current or voltage. So if you're talking about power, it should be the 50% of the maximum. Okay? Next, so this one is called the bandwidth. Okay? So what's cutoff frequency and bandwidth? Okay? So cutoff frequency is the frequency at which the ratio of the output over input has a magnitude of 70.7%. Okay? So it is yeah, this point, this point. Okay? So again, if it's in terms of power, so you're looking for the 50% of the maximum. Okay? So cutoff frequencies determine at which your device will operate or will not operate. So it is like a boundary. Okay? What about the bandwidth? So the bandwidth is the range of frequencies where your device operates. So this one, this is the range wherein your circuit will operate as expected. So mathematically, bandwidth is equal to the difference of the cutoff frequencies. So you have the upper cutoff frequency minus the lower cutoff frequency. So that's equal to the bandwidth. Okay, next for the series RLC circuit, so let us apply resonance in a series RLC circuit. Let's have the example from the first experiment since it is a series RLC. Okay, again, current is maximum at the series resonant frequency. So let's solve for the resonant frequency. We have 1 over 2 pi square root of L times C. So let's just substitute the values. So 100 millihenry and 2.2 micro, okay, microfarad. So 1 over 2 pi square root of 100 milli times 2.2 micro. So the frequency, the resonant frequency is 339.32 hertz. So as you can see from this graph, okay, so the current for the resistor, inductor, and capacitor is equal because we have a series circuit, okay? And as you can observe, okay, at this point, around 340 hertz, we have the maximum current. So at 339, this is the exact one as computed. This is the simulation. You can zoom this if you want. So as you can see here, we have this kind of a waveform. Looks like a passband. So at this point, the highest peak, if you're going to trace the frequency, so it's around 340 hertz. So 339 or 340 hertz. Okay, so that's it.